Okay, now we want to look at the idea of constructing a composite. We've already, in class, we already saw how we can construct a chain of values. We started with a value of x, and then based on that in Excel, we calculated a value of another value, another column based on what was in the x column according to a rule. The rule was that the value we got was negative x squared over 2. Okay, that's not actually what we're going to use here, but we saw that a value of x could give us a value of u, and then we could take that value of u and calculate a value that we call f according to a different rule. So we can apply one rule to x and then another rule to the result of that. We've got a chain of values, and we could continue that chain. We could take the values of this thing and calculate with a different rule some other value, and so on and so on. And when we do this with graphs, as we're going to do here, and I'm going to show you how that works, we get really what we call a chain of functions, the functions represented by the graphs. Okay, so we're chaining functions here. So we're going to chain two functions. We're going to chain a function u of x. U is a function of x here because, of course, if you've got a value of x, you can figure out the value of u. So we got this function u of x. So for every value of x, we'll calculate a value of u, and then we'll use that value of u, because right here is a u axis. We're going to use that value of u to determine the value of another function f, and here's the graph of that f function. And then we're going to construct a function that shows the value of f versus a value of x, the value that we started with. So we graph f versus x. There's this intermediate u function that's used to aid us in finding the value of f that goes with the value of x. So what do we do? Well, we've got the x scale here, and we got the x scale here. Same scale on both graphs. So I've coded these lines and points by colors, green, orange, blue. And over here it's green, orange, blue. This point on the x-axis here indicates a value of x, obviously. If we go to the same value of x here, then this line segment here represents the value of u. I mean, we could project up and over here. We'd get a value of u here on the axis, but that value would be the same as the length of this line segment, or would be represented by the length of this line segment. So we take that value of u, and now we put that value on this u axis. And of course, since this u axis goes this way, we've got to turn that line this way. So we did that. So right here's a little segment. It has the same length as this one, or it's supposed to have the same length. Obviously, I'm not going to spontaneously draw the length exactly the same, but they're reasonably close. Okay, so for this value of u, which we represent down here now, we find the value of f. So what have we done? We've taken a value of x that we got from here, but we accessed it over here on this graph. We found a value of u. We use that value of u to find a value of f, and the value of f is the length of this segment, which I've indicated by a green line segment with a kind of a tick mark through it, a little line through it, to indicate, to differentiate it from any of these other lines. So we take this value now, that's our value of f, and we put it over here, and now we have the value of f that goes with this value of x. Now we go to the next value of x. Okay, right there's the next value. Okay, well, we come over here to find what the value of u is going to be so that we can put that in and get the value of f that goes with this value of x. Okay, so there's the value of u that goes with this value of x, and we put that on the u-axis down here, and we find the value of f that corresponds to that value of u, and that's the value of x that corresponds to the original value of x. So we put that line here. And the graph is going to go through the point at the top of this line, the point at the top of this line. Now we go over to our third value of x. So that's going to occur on this x-axis, same place it would on this x-axis. But now it's going to be evaluated in terms of this function u. And you see that the value makes a big jump here, because this graph is concave upward. It's increasing at an increasing rate. So here's our new value of u. So, well, we got to bring that down here, and that takes it all the way over here on the u-axis, and we only get a tiny value of f. So we just get a tiny value over here. Now, we can also do that, of course, for the point where x equals 0. So here's x equals 0. And here's x equals 0. Now, x equals 0 is at the origin, of course, on the x equals 0 point on the x-axis is the origin of the coordinate system. And it turns out for this function u, which is a power function with a positive y factor bigger than 1, we find that this point is just the origin. The value of u is just 0 at this point. Well, that means when we put it on this axis, its value is going to be 0. And the value of f then is going to be the value of f when u equals 0. It's going to be this. So we have that value over here as well. So what we do is we sketch the graph through these points, and we get a graph that looks like this. And I didn't have this, and I asked the class, well, what does that look like to you? And somebody responded, well, that looks like the right half of a normal curve. If I reflect through the x-axis, I get the left half of the normal curve. And this is really a construction of a normal curve. If this is the squaring function, and this is an exponential with a negative doubling displacement, then what we get over here is a normal curve. And there will be a standard deviation and so forth, and we'll learn later how to locate that standard deviation and employ this normal curve in making real-world statistical references. That's not the word I was looking for, the word inferences. Kind of late, getting hungry. Okay, there we got it.